In this lecture, we're going to introduce our first set of inequalities called cover inequalities. Our context is going to be a feasible region defined by exactly one constraint. In this case, all the x variables are going to be binary, 0, 1 variables. We're going to have a single constraint where we're going to assume that all of the constants are greater than or equal to 0. If they're not greater than or equal to 0, we could just do a change of variables and replace x with 1 minus x. We're also going to assume that our right-hand side vector b is also greater than or equal to 0. The key component to a cover inequality is a cover. We say that A is going to be a cover if the sum of all the constants in the set A is greater than the right-hand side vector b. We can kind of get an idea of what this is saying. A is going to be a cover if all of the x's inside of A can't be set to 1. If they were all set to 1, then the sum of the constants would be greater than b and our constraint would be violated. We say that A is going to be a minimal cover if by removing any element k out of A, we no longer have a cover. That is, the sum of the constants after removing one element is going to be less than or equal to b. The key idea of the cover is that if A is a cover, not all of the x's inside of A can be equal to 1. If they were, then our constraint would be violated. So we can write a constraint. The sum of the xi's in our cover set, A, has to be less than or equal to the size of A minus 1. That is, at least one of these x's has to be equal to 0. This is exactly what this constraint says. This is the basic cover inequality. We can extend this, though. The first way we can extend these cover inequalities is by extending the idea of a cover. We're interested first in a set that's a cover set, and looking at all the elements inside of this cover. However, we can extend the cover to E of A. This extended cover is going to include a new set of constants, or rather a new set of indices, so that all the constants in the extended set are greater than all the constants in our cover set. To be more precise, E of A is an extended cover, where it includes some cover set A, and also all the indices J associated with constants that are greater than every constant inside of our cover set. It's easy to see that this constraint is valid inside of our extended cover, or for our extended cover. If we can have at most cardinality of A minus 1, xi is equal to 1 inside of our cover, then the same is true of our extended cover, because all the constants in the extension are greater than the constants inside of our cover. We can verify this to ourselves with a simple example that I'll leave as an exercise. The idea of extending a cover is interesting, but not particularly powerful. A more powerful technique is called lifting. To lift a cover inequality, we start with a cover inequality defined by cover A, and then we pick a particular index J that's not in our cover, so that A of J, the constant associated with this index, is less than at least one of the constants inside of our cover. In effect, this index J is preventing us from extending the cover by J. To lift the cover inequality, we're going to introduce this new index J into our cover set A, but we have to have a particular multiplier alpha J associated with it. This multiplier can be thought of as a penalty for how much this constant AJ is less than the other constants inside of the cover. Our goal now is to find the constant alpha J so that alpha J times xj plus the sum of all the xi's in the cover is less than or equal to the size of A minus 1. That is, we have our initial cover inequality we'd like to introduce this index j, and we'd like to find the multiplier needed in order to introduce this new index. To find this value alpha j, we think about the different values that xj can take. If xj is equal to 0, then alpha j can be anything. That's because when x of j is equal to 0, we just have a valid cover inequality remainder. And so it's valid, and we can do anything we'd like. If xj is equal to 1, we're in a more interesting case. In this case, since xj is equal to 1, we have our set of cover variables, I and a, less than or equal to the size of a minus 1 plus some constant alpha j on one side of this inequality. This inequality has to hold for all the x's that are in our initial feasible region. Although this inequality has to hold for every x inside of our feasible region, we're going to focus on a particular smaller region that we're going to call the remainder. The remainder region is the set of all x's that satisfy our original constraint, but augmented by the constant associated with the index j. We can think of the remainder region as the region of feasible x's after we've set xj equal to 1. This remainder region is going to allow us to talk about how much of the other x's we can put into our region, given that xj has to be equal to 1. In particular, we're going to define a constant r, and r is going to be the maximum that we can achieve over all the x's inside of this remainder region. We can think of r as being the maximum number of x's that we can set equal to 1, given that xj is equal to 1. It's not too hard to see that after we define this r, the value of our alpha j can be defined in terms of the r. Specifically, alpha j is equal to the size of a, our initial cover, minus 1 minus r. To get a better intuitive understanding of why this should be the value that we set for alpha, we think about our initial constraint. We'd like this constraint to be satisfied for all x. In this case, our size of alpha minus 1 is going to stay a constant. And we know that the maximum value that the sum of the x's i's can take is going to be at most r. By transferring this r to the other side, we get the value for alpha, so that this value of alpha is going to keep this constraint feasible for any value of the x's in our initial feasible region. Effectively, what we've done is we found a maximum value for the sum of the x's, given that xj is equal to 1, and subtracted this from the right-hand side of this constraint. Because this r is defined as a maximum, we know that this alpha j is going to induce a feasible constraint for any set of x's. But we should be a little bit careful. In order to define this value alpha, we have to solve a maximization problem. Specifically, we have to find this value r. It's not too hard to see that this turns into a knapsack problem. We're looking to maximize the sum of the x's subject to this particular constraint. The sum of the x's has to be feasible for this remainder region. This remainder region is defined by b minus our constant aj, and we'd like to find binary variables. This is just the binary knapsack problem. We should note that in this knapsack problem, the only place that j actually figures is as a constant on the right-hand side vector, b. And so the impact of j on this knapsack problem is pretty minimal. We can exploit this minimal impact and consider some sort of technique that iterates this lifting procedure. So far, we've talked about just adding a particular index j to our cover. However, We could be in some situation where we've already included several of these indices and included many of the different alphas. We'll call this set of indices the lifted indices and denote it by L. We can solve a new optimization problem where we find the value R that maximizes the sum of the lifted indices plus the sum of our original cover indices, subject to introducing some new constant alpha j. So we can consider, after lifting this constraint once, we can lift it again, and we can continue lifting this constraint, each time including a new index j, and keeping all of the old indices in our objective function indexed by L, the currently lifted indices. This lifting procedure is actually very powerful. First, we should note that among cover inequalities, there can be a lot of them, potentially an exponential number. But what's nice is that after we lift these cover inequalities, the initial inequalities, by adding all of these new indices with new alphas, the constraints become facet defining. The constraints become facet defining after we've included every possible index. Because these constraints are facet defining, they're very powerful. And so now we should ask ourselves the question, can we solve the separation problem for them? That's what the next lecture is going to be about.